So we started section 6.1 last time, looking at the set of rational numbers. And I want to talk just briefly about some origins of these kinds of numbers. So Egyptians are credited with having used fractions. All of their fractions actually have numerators of 1, which is a little interesting. So instead of writing a fraction as like 7/12, they would have written it as a sum of fractions with numerator 1. And I'll tell you what, I'm glad we're not doing it that way anymore because that sounds a little bit complicated to me. So that's what they did. The Greeks adopted fractions with denominators of 60 from the Babylonians. We still use those kinds of 60 base measurements in angles. We see it used in like the Babylonians, and their enumeration system entirely had this base 60 business going on. And then every now and then you'll see something funny where people act like our number, they'll talk about, did you know what they taught my kid in school today? The Hindu Arabic numeration system. That's just crazy. That's the system we use. We use something that was derived from the Hindu and the Arabic. That's what it's come from. So the Hindus actually developed the modern bar that we used between the numerators and denominators. So that's where that came from. Came into use in Europe in the 1500s. So this stuff goes back a long way. We've been working with fractions a very long time. There's 3 different models, and we've seen 2 of them over here. We saw 2 different kinds of models. One model that we saw over there is called the area model. And it's the use of a rectangle, although you can use a circle and other things too, but rectangles are pretty common, to shade a portion, and you shade a portion of the rectangle. So we're going to do the example with 1/4. So if you're going to do an area model for the fraction 1/4, you're going to draw a rectangle. Again, it could be a circle or something else too. The rectangles are pretty common. And come on. You're going to split it into 4 pieces. So you can split it in half like this. If you want to split it like this, you can. Or if you want to split it like this, you can. It doesn't matter. You're just going to make 2 pieces into 2 pieces. And then you're going to shade in one of them. So that's a area model. It's a single shape with a portion of it shaded in. Okay, the purpose or the point of it is it's a single shape. The next one is a number line model. We haven't seen this one yet. This one's unique at this point. So again, we're going to use the same example of 1/4. So with a number line model, we have a number line. And it starts at 0. And for the purposes of the fractions we're working with, it's going to end at 1. And you're going to subdivide it to have 4 pieces inside. So 4 is a nice one because you can do it in halves and then in halves again. And each one of these hash marks is a fourth. So this is 1/4, 2/4, 3/4, 4/4, which is otherwise known as 1. So this one would be 1/4. And then we would mark on that number line the point that we're working with, 1/4. The last model we saw one example of last time. It's the set model. And it uses chips where some are shaded. So what you see is objects, so you can think of like poker chips, right? Where, that's not what I meant to do. Where you have, in this case, 4 of them. The number of them is based upon the denominator of your fraction. You want to draw them approximately equal in size, and then we shade in one of them because it's 1/4. They're all useful in their own right in different situations. Some things just lend themselves to one of these pictures better than the other one, right? If you're talking about 1/8 of my children and I have 8 children, that's a set model, right? They're individual objects. If I'm talking about 1/2 of my whole family, that's an entire object that makes more sense as an area model, right? Anytime we're measuring something out, number lines make a lot more sense. So they all have usability in their own place. All right, we're going to go through several different theorems in this section next. The first one's called the fundamental law of fractions. So we're going to let a over b be any fraction, and n is any non-zero integer. then A over B is equal to A times N over B times N. And sometimes we think about this in reverse. That's actually what simplest form comes from. So we take something that's in a form like AN over BN and we say, hey, look, it can simplify or reduce. Those n's can just be canceled, right? And we cancel the n's out, right? We reduce or simplify the n's out and it becomes the A over B. So these are two different versions of the same thing. Simplest form, however, is created when the A and the B have nothing in common. So this is telling you A over B is in simplified form if B is positive, so denominator is positive. And the greatest common divisor, this comes from a previous chapter of the book. If you've had number theory, you've seen this notation. If you haven't, it's not a big deal. But it's just telling you that the greatest common divisor is 1. Or, equivalently, they're just saying that A and B don't have anything in common. Okay, they can't have anything in common that divides them both. So we're going to write 3 fractions that are equal to 7 over negative 14. So take a minute, write 3 fractions, any 3 fractions you'd like to write. Once you have your 3 fractions, find somebody nearby and just see what they wrote. Okay? Agree with them, disagree with them, that's fine. Look at the differences in the things that you have created. So you're going to find different fractions that are equal to this one. Sorry. Check in with somebody nearby if you haven't already. All right, somebody tell me one that you have. Any of them that you have. Yes, ma'am. 1 over negative 2. Do others of you have that same one? All right, so that's a reducing one you did, right? Okay. What else do you guys have? Yes?
14 over negative 28.
14 over negative 28. So that's one where you multiplied by 2 on the top and the bottom. Yeah? Something else. Well, here's something cool. When we did the 1 over the negative 2, you could actually use that to create other things too. Did anybody do that?
Yeah, I had 5 over negative 10.
5 over negative 10.
I have 9 over negative 18. And 3 over negative 6.
Okay. You know what else you can do? You can multiply by a negative on the top and the bottom. So you could actually end up with negative 3 over 6, right? Yeah, there's got to be a negative, but it doesn't really have to be in the denominator. Equivalently, if you multiply by a negative number, it will create the negative in the numerator. So there's infinitely many ways that we could write equivalent fractions to these. Now, I'd like to take a look at this one. 42 squared over 35 squared. It's really tempting to do what? Do you know? Just cancel out the squareds. Actually, my Calculus 3 class, it wasn't this problem, and it wasn't quite the same thing. But they tried to do a similar sort of thing today in a problem they did. They tried to do something to the top and the bottom of a fraction that doesn't work. Right? It's just this innate sense that I should be able to reduce something because we have the ability to reduce multiplication. Right? We can reduce multiplication. And in some sense, squaring is multiplication. The problem is that when we would try to cancel a squared, the multiplication that's here, before we do so, actually looks like this. So there is multiplication, but it's not multiplying by the same quantity on top and bottom, right? So we have to be a little more careful. This is one way to express this version, and then we could actually look for some reducing between the values. Now, we could either simplify this further, like we could break down 42 and 35, or if you simply know what 42 and 35 both divide by, we can do it here as well. So does anybody recognize something that 42 and 35 both divide by? 7. So I could actually divide 42 by 7 and get 6, and 35 by 7 and get 5. And if I do it to one pair, I could do it to the other pair just as easily. Now, do 6 and 5 have anything in common that they reduce by? No. So there is no more reducing that can be done. And at this point, we would go back and multiply what remains. So I have 36 over 25. And we don't have to check if 36 and 25 reduce. We already know they don't because we had them in simplified form before we multiplied them. 6s and 5s, right? So because we simplified the form first, we don't have to do it or worry about it now. All right, equality of fractions. This is Theorem 6.2 is one of 4 ways we're going to look for fractions to be equivalent. If you have fractions that are equivalent, a over b and c over d, that happens if and only if you can cross multiply. Right? If the diagonals multiply out and they're equal, then the original fractions were as well. So you can see them right here. Here's one of the diagonals, a and b, a and d, and here's my other diagonal, b and c. Okay? Now that's only one of 4 ways. So we're going to actually take a look at an example, and the question asks us to show or to decide if the fractions are equal. So we'll do Theorem 6.2 first as our first way, but I want to show you that there's at least 3 other ways that you could do this problem as well, and all of them are equally valid, and depending on the values, may be preferable. So on this one, we're going to check. The first way is the Theorem 6.2 way. So we have negative 3 over 12. Sorry, you know what? Let me do this. Notice they're both negative. Agreed? So I don't really care to keep the negatives in the process of what I'm doing because they're both negative. They match in that regard. My concern is whether 3 over 12 is equal to 36 over 144. So I'm ignoring the negatives right now because I know those parts are equal. We're just going to work with the other pieces. Notice I put a question mark sort of above the equal sign. I cannot assume that these are equal. That's what I'm trying to show. So I'm sort of questioning, are they equal? And I'm questioning if they're equal by multiplying by the diagonals. So I've got 3 times 144, and I've got 12 times 36. Now, if you have a calculator, feel free to grab that and get that out. But I'd also kind of like you to think about the fact that if you were teaching this in that 6th grade class or 7th grade class, they may not have calculators. They may not be at the point where you're allowed to use them more consistently. So in this particular problem, this multiplication is not the most fun multiplication ever, right? That makes this particular method maybe not the preferable method on this problem because it's not real fun. I mean, the multiplication's a little bit big. For the purposes of what we're doing, it works just fine. You're welcome to grab a calculator. What is 3 times 144? 432. And what is 12 times 36? 432. So at the end of this, they are in fact equal. So since they are equal at the end, this Theorem 6.2 tells us they were equal at the beginning. So these are equal fractions, okay? Okay, so that's sort of method number 1. We'll do method 2 underneath it. All right, method 2, let's see which one I want to do next. Let's do simplify as our second method. Oftentimes when we're comparing fractions, they're not in simplest form. In fact, if they are in simplest form, it's really easy to know if they're equal because they'll look exactly the same. So if we can put them in simplest form, which means making the fractions smaller on top and bottom usually, that's often a helpful way to do it. And this one, I think that's actually the easiest option. This one I think is the preferable method for these particular fractions here. So we're going to do 3 over 12. And what will 3 and 12 both reduce by? 3. So I can divide them both by 3. 3 divided by 3 is 1. 12 divided by 3 is 4. That one's in simplest form. 1 and 4 don't get any simpler. But I have 36 and 144, right? You may not recognize that they both divide by 36. They do. But, I mean, I wouldn't necessarily look at that and go, hey, look, they can both divide by 36. Probably wouldn't think about that. What do you notice is the biggest thing they might be divided by? Probably 12s. If you don't see 12s and you see something smaller, that's fine. You could go with 2. That's what my son would do still. He'd just look at it and go 2. And he'd go 2 again. And he'd go 2. However many times there are 2s, and then he'd go to the next one. There's nothing wrong with that. It's going to take a little longer, but there's nothing wrong with it. So if you notice it's 12s, that's great. 36 divided by 12 is 3. 144 divided by 12 is 12. It's not simplified here yet, but you kind of know that the answer is yes now because the 3 over 12 is what the other one started at, right? So we can finish it out by dividing them both by 3 to give you the same 1 over 4. So again, since they both reduce and simplify to the same quantity, then they were originally the same value as well. So that's method 2. Method 3, we're going to find a common denominator. So when we say common denominator, it literally could be anything that they have in common, but the simplest way to find a general common denominator is simply to multiply the two denominators together. That's really ugly in this one because the denominator is going to get really big. Okay, but it is a strategy to use, and it does work really well in some cases. So we're going to do it as an example here, 3 over 12 and 36 over 144. And what you do is you multiply the 12 by the 144, and you multiply the 36 and the 144 by 12. These are big ones. So what is 144 times 3? 432, we did that before. What is 144 times 12? Okay, 1,728. How about 36 times 12? 432. And then I know I have the same denominator because it's the same numbers the other one was. And of course they're the same, right? So since they're the same at the end, they were equivalent at the beginning. So these are equal. It's common denominator approach. Okay, the last one we're going to do is a least common denominator approach. So least common denominator means that we're going to try and find the denominator that they match first, or they match first. So when we compare 3 over 12 and 36 over 144, I hope you look at this kind of like we did on the simplify one and recognize that 12 can be multiplied by something to get 144, right? It's simply, 144 is a multiple of 12. So I don't need to change the 144. I'm just going to change my 12 by multiplying by 12. So I have a 144 here. This is also probably just as easy as a simplify one on this one. And I have my 144 here. And then 3 times 12 is 36. So once again, they're equal. So it's equal at the end. So why do I tell you all these ways to do the problem? So sometimes you're going to be asked to do a specific method. Like it could say, right, determine if they're equal by simplifying. It might tell you which one to use. Sometimes it's going to make it just open-ended, and I want you to have options. But the real reason, the big reason that I teach you multiple ways to do it is because Some of these ways are going to resonate with some of your students and some are not. And it's really frustrating for a student if you only have one method to do a problem, especially when oftentimes there's not only one method to do a problem. And so if you're teaching the class and you're teaching them how to do it with 6-2 and a kid's just not getting it, right, the numbers are getting too big, they're not really good at multiplying and they're not allowed to use calculators, right, then having a backup approach on how to do something and say, hey, this isn't working. Let's pause and let's try a different method can be really, really helpful for your students. So that's the real reason why we want to do it. All right, not only can we determine if fractions are equal, we can also determine which fraction is bigger than another one if they're not equal. And that's theorem 6.3. So it tells us that this is, again, one method, not the only method, but one method for deciding which of two fractions is larger when they're not equal. And it's a lot like the cross multiplication from 6.2. If you're able to cross multiply here, right, AD and BC, and the AD is bigger when you cross multiply, then the left-hand side's bigger. So the inequality direction stays the same when you do this too. So that's a very handy one. Again, not the only way of showing this. We could use any of these other versions, over here kind of that we had. They'll, where we get common denominators or something like that too, simplify things. Those are options too. But this is a really handy one and it's often very nice to use. The thing that it doesn't do, both of these, 6.2 and 6.3, is that they only compare two fractions. So if you're trying to put things in order that's 3 fractions big, they don't work very well. Because you can only take 2 at a time, and then you have to take another 2 of them at a time, and you might have to take a third 2 at a time just to get them all in the order in the right way. That's really tedious. So that's not always the best choice. So here's an example of one that's like that. You have 3 numbers. Now if I just covered up the 7/10, and you just looked at the first 2 numbers, you could totally use theorem 6.3. But with 3 numbers, it doesn't work very well. So any idea what might be helpful to do with these 3 particular fractions to decide which one's biggest and which one's smallest?
They have the same denominator?
Yeah, making them have the same denominator is a really good approach here. At least it is for these 3 because the denominators will lend themselves to that nicely, right? Denominators of 5 and 10 and 20 are all multiples of 5, so it works nicely. All right, so we already have the 13/20 in a form that's really nice. Let's take 3/5 and make it have the same denominator. So what would I need to do to get the 5 to be a 20? Multiply by 4. And if I do it on the bottom, I have to do it on the top. So this will give me what fraction? 12/20. All right, and then our last one of the 3 is 7/10. What would I have to do there? Yeah, multiply by 2, top and bottom. So the top and the bottom, what do we get here on this one? 14/20. Okay, it says ascending order. What does ascending mean? Getting bigger, like when you ascend a staircase. It means it's getting bigger. So we start with the smallest, okay? So this is meaning small to large. So which one of these is the smallest? 3/5. So the 12/20 is the smallest. I'm just going to label them right now. Which was next? 13/20. And last is, yeah, the 14/20, which is the 7/10. So these are the order we're going to put them in. And we're going to put them in order the same way that you all were giving me back your answers. So great job on that. The order that we're going to put them in, right, or the way we're going to write them is in the numbers the way they were given to us, not the ones we changed them into. So the first one, we're not going to write 12/20. We're going to write 3/5. And you can put a comma if you want. I'm going to put a less than sign because I'm going to show that the order is increasing by my signs, but commas will be fine. The next one was 13/20, which was exactly how it was given to us. And then the last one is 14/20, but it's represented as 7/10 when it was given to us. So this is the ascending order that we're looking for. Okay. On this one, we do actually just have 2 values. So we can use theorem 6.3 if we'd like. We're trying to decide if it's greater than, equal to, or less than that goes between these two. So we're going to use Theorem 6.3 because we haven't used it yet, but I'm also going to show you a couple other thoughts here that maybe are even different than what we've already done before. So if we're looking at this one and we're looking at the diagonals, we can do 21 times 215, and we can do 430 times 51. So big numbers to multiply. So again, maybe not the best choice on this one, but it's doable. What is 21 times 215?
4,515.
Okay, thank you. And then what is 430 times 51? Huh? A lot larger is the correct answer. Does anybody have the actual value?
21,930.
Yeah, a lot larger. So it goes like this. Remember, the direction of the inequality opens towards the larger value. So we can take that and we can go back up to the original value, and we can actually put them in the same way. 21 over 430 is less than 51 over 215. Now, I don't want to belabor the point and do common denominators or any of that kind of stuff again, but I want to show you something else that you can think of on this one, even if you're just wanting to sort of check to make sure that what you just did made sense, right? Making sense of math is really important because it should all make sense. And if it doesn't, then you might have made a mistake. So it's kind of a good check step. If you take a look at these numbers at the beginning, 21 over 430, it's close to being 20 over 400, right? That's really close. I haven't changed the numbers that much to get to that point. And if I were to reduce that, I can, divide both by 10. That gives me a 2 over 40. And I could divide each of those by 2, and I could get 1 over 20. It's approximately 1 over 20. The other one, 51 over 215, it's close to 50 over 200. Right? It's close. Not exact, but it's close. Again, you can divide them both by 10 to get 5 over 20. And 5 over 20 is actually 1/4 if you divide them both by 5. 1/4 is a lot bigger than 1/20. Or if you have a cake and you split them into 20 pieces, and you have a cake and you split them into 4 pieces, who gets more cake? The 4-piece one, right? As long as the cakes are the same size, they get a lot more. So you can also think about it sort of from a perspective of approximations. Now, that only works if the values are drastically different in size, right? If this had been 1/4 and 1/3 and my adjustments had not been quite right, I might not have yielded what I needed, right? But for this one, that is a good approximation step, or a good step to do approximation, just to see, am I on the right track? So the correct answer is a less than symbol. So it is that 21 over 430 is less than 51 over 215. Denseness. This isn't dense like my kids talk about. Nobody's dumb. This is dense in the sense that it has lots of stuff in it. If you've got any two rational numbers, any two fractions, there's always a number that's another rational number, another fraction in between them. So think about this. We'll use the numbers 1/2 and 1. We'll use 1/2 and 1. That's fine. So if you think of the number 1/2 and the number 1, there's always a number in between them. One way to think about that is about that sort of from a geometric perspective. Do you remember the midpoint formula? I'm not going to ask you to say it for me, but do you remember what I'm talking about? That there's always a way to find halfway something. So from that geometric perspective, if you're thinking about a number line, there's always distance between them, and you can always find the halfway point of the number line, right? It's going to be another rational number. The midpoint formula took two numbers, added them together, and divided by 2. That's what that did. And so there's always space between two numbers, and because there's always space, there's always another number in between them. So if you think about your calculator, you can sort of like zoom in, and it makes it look like it's much bigger, right? Just like your phone, right? You zoom in and everything gets larger. There's always space in between there that you didn't necessarily see before. Okay, so that's what this distance property is talking about. There is another way besides the midpoint formula to find a number that's in between, and this is really clever because the midpoint formula, where you add two numbers together and divide by 2, works really nice sometimes, and sometimes it's just awful because if you're going to add them together and they don't have like denominators to begin with, right, they're going to be messy. This is really clever though. What you can actually do to find a number in between two fractions is you can just add their numerators together, and you can add their denominators together, and that fraction will be in between the two fractions you started with. It's really easy to use. So when you have fractions that are the same denominator, it's fine. So like imagine that you had, like 2/15 and 4/15. Well, no problem. I can add those together and divide by 2, easy peasy, because the denominators match. But if you had an example, which is like the next one on our next slide, where you had something like 4/7 and 3/8, I do not want to add those together and divide by 2. That does not sound like fun. A denominator of 7 and a denominator of 8, that's no good. I don't want to do that. But I can actually do it in this way. So here's two awful denominators. You do not want to add them together and divide by 2. But there is a rational number between them. The denseness property said so, because there's always space in between them. So we can actually do what that theorem, what was the number? Theorem 6.5 said we could do. We could add the two numbers together on the top, so 33 and 7. We can add the two numbers together on bottom, 427 and 92. And what we find is going to actually work. And we're going to verify it just with a real quick step in your calculator. So on the top I have 40. What is 427 plus 92?
519.
519. So grab your calculator real quick. We're just going to look at some decimal approximations to sort of convince ourselves that this actually created something that worked, right? That's one of those check steps of reasonability. I'd like for you to find a decimal approximation for the three fractions that are here. So approximation for 33 over 427, approximation for 7 over 92, and one for 40 over 519. I don't have this one written down, so I'm going to do it with you. I think you're going to need 4 decimals. I'll do the first one. I have 33 over 427 as 0.0773 if I round. What do you have for 7 over 92? Okay, good. And how about 40 over 519? Okay. So is this one, in fact, in between these two? It is. I know we haven't talked about that in this class, but you've seen this before. It's in between there, right? Yeah, it's in between those two values. So it is, in fact, creating what we expected and were told that it would create. So our fraction's answer that we're looking for is 40 over 519. So why must there be a number between these fractions? Well, because they're dense. What does that mean? AKA. That's there. There is space between them. So space between them means there's a number value between them, a rational number value between them. Okay. We good for the next one? So when you get your homework, and if you see the homework on the bottom of the sheet, it'll tell you that you have problems that are A, B, C. A is section A in your book, and B is section B. C is called the connections section for your book. So I abbreviate it with C because that works really well, and it follows A and B, right? A, B, and C. Connections actually means that we're making connections to teaching. So sometimes there's problems in there that ask you to think about how you would explain this to a child or analyze an error that the student did. So those are the kinds of problems that show up in section C, and that's what this is on example 8. We have a student, and they've simplified m plus n over p plus n to m over p. And I want us to analyze a few questions. So when a student makes a mistake, sometimes they just made a mistake and they don't really think it's wrong. I mean, they just guessed, right? They just made a mistake. Sometimes there's a reason for it, though, and if there's a reason for it that we can identify and help them to correct that thinking, that's helpful. So what did the student actually do here? Yeah.
They, looks like they like canceled out the end since it was like the same like value.
Yes, they canceled out the plus n's. Does everybody agree? That is exactly what they did. Why might they believe that this is acceptable or correct to do? They saw that there are two n's. It's the same value. There is some times when we can do this. We can't do it here.
They're different signs.
It's not because it's a sign issue. We saw it already in this lesson today. When did we have cancellations of n's and it was acceptable?
Because you could do it to the MP too.
Not because it's M and P,
Or multiply.
because it was multiplied. When we saw it earlier in this lesson and we were able to mark out the n's or whatever the letters were at that time, it was a multiplication fact. This one's not multiplication, it's addition, right? So if this had said, for example, mn over pn, we do this all the time. Yeah. And so they've translated something that they know to be true with multiplication into a fact about addition that doesn't hold, right? But there's a reason for what they did. It wasn't just arbitrary. They remembered something that was valid, just the context was wrong. So that's what the student probably did, is that they remembered multiplication, simplification. And tried to do it to addition. Okay, so it's one thing to tell them you can do it to multiplication and you can't do it to addition, and you just need to remember that rule, and that's the way it always works. It's quite another to convince them why it should and shouldn't be true. Agreed? I can tell you, the sun is black, but unless you actually have evidence of it, you're probably not going to believe me that that's true. So we can tell them you can't just cancel out the plus n's, but showing them why it fails is probably a little bit more helpful than just telling them. So one of the ways to help in a situation like this is to show an example with numbers that fails. So we're going to make up an example, and we're going to hope it fails, because I'm just going to make it up with you. So for example, let's say that you have 1 plus 2 over 5 plus 2. If they were doing their operation, they'd cancel the 2's, right? And they'd have 1/5. Okay, so option 1 is that the 1 plus 2 over the 5 plus 2, we cancel these out and we get 1/5. That's what they believe to be true based on the work that they did above. Now, let's actually do the problem where we don't cancel it, but we simplify it because they're numbers and we can. So another option, if we simplify it and we actually add it, we get 3 over 7. Is 3 over 7 equal to 1/5? It's not. how could we show that if the student's like, well, maybe they're just equal then? Common denominator would be one way. What's another way? Cross multiplication. That'd be another way, right? They're actually in reduced form already. These two happen to be in reduced form, and the reduced forms are not equal, so you could also justify it using that kind of language if that's helpful to them. They're already simplified, can't simplify them anymore, and they don't match, so they're not equal. So this is actually showing them an example where it doesn't work. And if it didn't work in this example, then it doesn't work in general, okay? So showing an example, it's not a proof, but you can disprove something by example really easily, right? Disproving by example is really easy. Okay, we have one last example that's kind of an interesting one. This is another thing that kind of shows up sometimes in the connection section where it just takes an idea and it extends it to a different part of mathematics to show you an interesting feature. Okay, that's what it is. So if we take a set of numbers equivalent to 1/3 and we graph them as points on the xy axis, so the numerator becomes the x coordinate and the denominator becomes the y coordinate, what type of graph do we get? Okay, so there's a lot of information in that paragraph. It's not even a paragraph, but it feels like it, right? So we need to take it a bit at a time and create what it's trying to get us to create. The first thing it says is we take a set of numbers equivalent to 1/3. You know how to do that. We've done that today. So if I want to get some numbers equivalent to 1/3, can somebody give me another number it's equivalent to 1/3? 2/6. 3/9. Okay, and I want to actually do something that's negative as well, so I'm going to do -1 over -3. Okay, that's enough for what we're going to work with. If it weren't enough, when we do the next step, you'd know it. Okay, so we take some numbers that are equivalent to 1/3. The next thing it does is it says that we take each of those fractions and we make them an xy ordered pair. So this becomes the numerator 1, or the numerator 1 becomes the x coordinate 1, the denominator becomes 3. This becomes 2, 6. 3, 9, and -1, -3. Okay, does that part of the directions make sense now? Right? Numerator is x, denominator is y, it's a point. I have a grid set up over here, so I'm going to use my grid. Feel free to draw a graph in for yourself. We're going to graph these ordered pairs. That's not too bad. Okay, so we have the point 1, 3, so here's 1, 3. We have the point 2, 6. There's 2, 6. And we have the point 3, 9. There's 3, 9. The other point, the one that I created that was negative, is because I wanted to show that it does go into the negative part of the graph, is -1, -3. Okay, so those are the 4 points. If we were to connect these, what would it look like? Yeah, it's going to look like a line. So feel free to connect those. It's going to look like a line. It does have one caveat, though. So this appears to be a line. Do you know what the slope is of the line? Can you tell? Oops, sorry about that. 3. So if we take one of these points, we'll just take the bottom one and we go up 3 and over 1, right, rise over run. It appears to have a slope of 3. Where does it appear to have its y-intercept? Where's it across the y-axis? At the origin, right? There's a problem with that, though. What's the ordered pair at the origin? 0, 0. It doesn't fit in with this description, does it? 0 over 0 is not 1/3 like everything else was. So our graph actually will have a hole in it right there. at the origin. Because it doesn't work. It doesn't fit with the description. So this would be a slope with line 3 and hole at 0, 0. It's got this one little weird thing to it, right? That one little 0, 0 that's not really what was supposed to be based on the description. But every other point along the line would be in the ratio of 1 to 3. So even these random points, like if you take a point, say, right here, see my orange dot right there? It's not on any whole number, but if you still found those decimal values that it was at, right, or those fractional values that it was at, it would still have the same ratio of 1/3. But 0, 0 doesn't. All right, that's the end.